Right, today we've got to lecture 10 now, and let's just get into it. We're talking about simple elevated reinforced concrete slabs. When I talk about a simple elevated reinforced concrete slab, you walk around town and you see multi-story buildings, and multi-story buildings stand on columns and beams, and they're slabs. Those are the floors that the occupants of the buildings use to move around on. That's pretty straightforward. Now, there are, we're looking at a one-way slab design today. Next week we'll be looking at two-way slab design, but just to enlighten you regarding one-way slabs, if we looked at slabs and we looked at a single isolated slab that was supported on four sides, like this, or a multiple series of slabs, each one supported by a beam around the edge, we could classify those as two-way slabs. In other words, the statics and the mechanics of it allows it to span that way and this way. And the bending moment will always be greater in the shorter direction where a slab is supported on four sides. And we'll be doing that in the next session in lecture number 11. But that only holds good for this sort of ratio. If that is two, if there's 2 units, then that's 1 unit. Once this dimension gets more than twice this dimension, then the slab just tends to span one way, like that. And that's what we're looking at today. So we're looking at slabs that are only supported along there and along there in a simply supported case. So in other words, we're looking at slabs that are supported like this, and that's a span, L, with a uniformly distributed load perhaps. And what we do is we look at a 1 meter width of slabs. So if you had multiplicity of slabs, as we're going to be looking at in our tutorial, a multiplicity of slabs all spanning onto beams, these dotted lines are the beams underneath, there the ends are, and supposing this was 15 meters, and each one of these was 5 meters, each span between the beams, 5 meters, 5 meters, we would say that the actual, looking at a side elevation of it and drawing the idealized diagram, there our supports are, which are the beams, 5 meters apart with uniformly distributed load on. And what we're doing today is we're going to design a 1 meter strip of slab, 1 meter wide strip. Just a 1 meter wide strip, because if we can satisfy the criteria for a 1 meter wide strip, we can satisfy the criteria for a 15 meter wide strip. So that's just a bit of enlightenment, I hope. So we're looking now at a one-way slab, this one there, spanning 5 meters, resting on brick walls. And when designing simply supported or continuous slabs, assume a depth for the slab using standard span depth ratios. And these are standard span depth ratios, and sometimes you do a bit of a thumb suck. You do the problem, it doesn't work out accurately, so by a process of iteration, sorry, I should have added it down there, you look at these ratios, span to depth, but often the engineering designer comes up by doing a series of iterations until he gets a slab that's economic, doesn't have too much steel, too little steel, and so forth. But with years of experience, you get to be able to make a very good judgment and probably get it right the first or second time. Incidentally, I've taken a guesstimate at making the slab 210 millimeters thick in this case. So when designing simply supported or continuous slabs, assume a depth D for the slab, and D is the overall depth of the slab, using standard span/depth factors. Unit width of slab is used, 1 meter, and that's what I just illustrated to you. And the positive and negative steel is computed as previously shown for beams, but for unit width, for a 1 meter width. Shear is checked in the usual way. It must be noted that shear stresses are usually low, except when a heavy point load is applied. Compression steel is virtually never used in slabs. So the slab we're looking at today has the following specification. It has a live load of 3 kilonewtons per square meter, or 3 kilopascals. Ceiling and floor finish. That's a suspended ceiling underneath. Maybe there's a floor covering. Maybe there's a cement screed on the concrete. That comes to 1 kilopascal, 1 kilonewton per square meter. We're using concrete strength of 32 MPa. And we've got an A1 exposure, which, as you all will remember by now, gives us a 20 millimeter cover. So in the solution, the slab weight, 210 times 24 kilonewtons per cubic meter. The slab itself weighs 5.04 kilonewtons per square meter. So the dead load then is the weight of the slab of 5.04 kilonewtons per square meter plus the 1 kilonewton per square meter for the ceilings and this floor screed, all multiplied by 1.2, which is our limit state factor for dead load, plus the live load factor of 1.5 multiplied by the actual live load of 3 kilonewtons per square meter. And this gives us a total load of the slab, live and dead, factored up, of 11.75 kilonewtons per square meter. So our bending moment is back to the perennial WL squared over 8. Remember, for a 1 meter width strip, 1 meter wide strip, that's why I've left it. You could say 11.75 by 1 by 5 squared if you wish, but we're working on unit width. Gives you a bending moment of 36.72 kilonewton meters. Assuming 12 millimeter diameter main steel and 20 cover, which is the cover stipulated for A1 exposure, we get an effective depth of 184 millimeters. There are 20 millimeter cover is, there are 12 millimeter steel is. We take the radius of the steel, 26, off to 10, gives us 184 millimeters. From the chart, we can check the effective depth, and you can go at that in many ways, but what I've done here is I've assumed a steel ratio of 0.01, which isn't particularly high, but a steel ratio of 0.01. If you look at your chart, and you've got a steel ratio of 0.01, it's up there somewhere. You go down to 32 MPa and you come down to your M over BD squared, which is 3.5. From that, you can compute your effective depth from the formulas that we've been using. The root of the moment divided by the by lambda, which is M over BD squared, times the breadth of the beam, which is 1,000 millimeters, as it turned out to be, 1 meter wide. So the depth is the moment in kilonewton meters turned into newton millimeters, divided by lambda multiplied by the width of the section. The standard width for slabs, 1,000 millimeters, 1 meter. And from this we get a depth required of 102 mil. But I can assure you, if you made the slab 102 mil, you'd have a deflection problem. It would sag, and it wouldn't work very well, especially if it was a roof slab. After rain, you'd have pools of water standing all over it, and it gets worse in time, so we'll err on the high side, yeah? So we use an effective depth of 184 millimeters due to deflection problems, or perceived deflection problems. Now the actual M over BD squared is 36.72 turned into newton millimeters, divided by the breadth of 1,000 millimeters, the breadth, multiplied by the effective depth squared. It gives us an actual lambda of 1.08. If you look on your chart, I'm not going to pull it out now, you guys should be very familiar with this. I'm sure you've all been working very hard at your lecture notes and your tutorial notes, so you'd be very familiar with this. So from the chart, the area of steel over BD is 0.002, which is P, of course. And that would be 0.002, which is P, by the breadth of the section, 1000 millimeter strip, by 184 for the effective depth, 368 square millimeters per meter width, which we're going to use N12s at 250 centers, where our area is actually 440. A thing to bear in mind is that the code says you cannot have bigger bar spacings, either for temperature steel or for your main steel, bigger bar spacings than twice the depth or twice the thickness of the slab. So we couldn't go more than 400 millimeters in this particular case. But if you keep your bars pretty close together, you have far less cracking. We now can check our shear capacity. At the support, the shear force equals the total load multiplied by 4.7 over 2. That's the effective span inside the supports. Just to clear that up with you. That's the effective span inside these supports, often referred to as Ln. Ln is this dimension there, from there to there, that's Ln. Okay? This is the actual design span, that's Ln. So we use Ln because that's the shear at the support. Total load divided by 2, 27.61 kilonewtons. The shear capacity with no shear steel at all, only your main steel that we've just selected, of those N12s at 250. From that, working through your normal shear calculations, as we did previously, looking at shear, you'll find that the shear resistance of this slab is 51 kilonewtons, which is far greater than the actual shear force. So you don't need any shear steel at all. That positive steel running through the bottom of the slab is more than adequate. Now the transverse distribution, temperature steel, whatever you want to call it, used to be called distribution steel, now often called temperature steel, but that's a steel that runs in the other direction. It's not structural. It stops cracking, is 0.002% of the area of steel, of unit width of the slab. So from the code gives you these factors. So 0.002 times the breadth, which is 1,000 millimeters. We're working on the strip, 1,000 millimeters wide, by the overall depth, 420. We use N12s, 250 centers gives us 440. So we can run N12s the other way as well. And if you look back, your main steel is, in this particular case, also happens to be N12 at 250. So you end up with a mesh of steel of N12 bars at 250 centers running both ways. We have an exercise here. Redesign the slab in the previous example using a live load of 5 kilonewtons per square meter. So I have done that, as I recollect, in the tutorial. And then the second question was design a 3-span one-way slab with each span being 6 meters using the moment and shear factors as found in AS 3600, referred to on that page. This is the loading, but I shall go through that in more detail when we get to doing the problem. Here are a couple of examples of the curtailment of steel reinforcement. On a simply supported slab, single span, as we've just done, the code says that at the center, in the center area, you have to have the full area of steel, but you can actually stop some of the bars off at 0.2 of the clear distance between the supports before you get there, in the name of economy, because the bending moment is virtually nothing when you approach the support. So you can actually, those little things things there show that's the end of the steel. You don't bend the steel up like that. They indicate in a drawing that the steel bar ends at that point. So you can then run 50% of this total area through onto the, in other words, your N12s at 250 will go through to there. And over there, your N12s at 500 will go through to there, because in this section here, you've got N12s at 250. That's already selected. If we run every second bar through to the support, which gives us 50%, we'll have N12s at 500 running onto the supports. Bear that in mind. You can do that in economy. I haven't done it in any of the examples, but the code says you can do it, and they're quite right, you can. Looking at a continuous slab, which is what we'll be having a look at today as well in the tutorial, a 3-span beam, is that these are the dimensions. Your negative steel must run into the span by a distance of 0.3 of this clear dimension. I usually just work to the centers of the supports, which is adequate as far as I'm concerned, but to be strictly speaking, you should work from the face of the support for a distance of 0.3 of that dimension, if you know the width of your supports and so forth. So we've got 100% of the steel in the middle where the maximum moment is. It's curtailed there at 0.1 of this dimension away from there. So we've got 50% of this steel running onto the support, positive steel, and 50% on there. This is the negative moment, the hogging moment, because you know that your beam bends like this over the support, and that's the negative steel. Again, these are the curtailment figures for negative steel, because the negative moment drops off sharply, as you all know by now. So note, these percentages relate to steel areas. And if you're doing a single job, sometimes you wouldn't, a small job where it doesn't matter, you probably would just run all the steel through for the full length. But if you're doing a 100-story building, of course you're going to save a lot of money by working exactly to the code and using less reinforcing steel. Right, let's move on. AS 3600 7.2 provides bending moment and shear force coefficients for the design of continuous members. The design moments and shears found using these coefficients can then be used to find suitable sections and reinforcement by applying the methods previously illustrated. See the next page. So the simplified method for reinforced continuous beams and one-way slabs, as I said, not two-way slabs, we'll be dealing with those in the next lecture. Clauses 722 to 724 may be used for the calculation of design bending moments, shear forces for strength in continuous beams and one-way slabs of reinforced concrete construction, provided that the following rules are met. The ratio of the longer to the shorter length of any two adjacent spans does not exceed 1.2. And what they're saying there is that, I'll show you, that if you've got two adjoining spans like this, that ratio, the difference between the two, must not exceed 1.2 between those two spans, span 1 and span 2. So you can have a variation in those dimensions. You can, B, the loads are essentially uniformly distributed. It has to be UDL across the whole thing. The live loads do not exceed twice the dead load. Okay, so you have to check that out. Members of uniform cross-section, they don't change in depth or width or anything, because this applies to beams as well as to slabs. So the members are of uniform cross-section. And there are cases where beams, for instance, don't maintain a constant cross-section through the full span of the beam. The reinforcement is arranged in accordance with these requirements of the code as applicable, as far as maximum spacing, minimum spacings, all that sort of thing. And the bending moments and supports are caused only by the actions of a loads applied to the beam or slab. So there's no external bending moment at the supports. I'll just run you through this then. The negative design moment. So let me just make a sketch of that so that I can do it a bit more neatly. I'm just drawing it off camera. I'll do 4 spans in this particular case. 4 spans. So where we've got 2 spans only, the moment, if there were just 2 spans, the moment at the first interior support, and that is the first interior support of a 2-span beam, this one there. The moment there is the total load on one span, which they've called FD, I'll call it W, times the distance, the span of the beam squared, WL squared. So what we've got is WL squared over 9. That's what that ends up being. That's all these factors are. The WL squared over 9, WL squared over 10, WL squared over 11, etc., etc. Not rocket science. When you've got more than 2 spans, then the moment that the first interior support is WL squared over 10. So it would be WL squared over 10 the moment at the support. And you'll see that when I do the tutorial. At other interior supports, WL squared over 11. So on a 4-span beam, this is the other interior support. So the moment's even less there, WL squared over 11. And at interior faces of exterior supports for members built integrally with their supports, for beams where the support is a column, WL squared over 16. We're looking at slabs today, where the support is a beam, WL squared over 24. So you could get a negative bending moment there of WL squared over 24, sorry. In the tutorial that I've done, I've ignored the moment there. I've assumed that it's simply supported on a brick wall. So I've ignored that moment. Now those are the negative moments. So I'll just draw those in. I've assumed that it's nothing there. It's that there. It's a bit higher there. It goes back because it's symmetrical. It goes to there, and then it goes back down to there. So this here, at the first interior support, more than 2 spans, WL squared over 10, where it's W per unit length for 1 span of beam, not for the whole thing, just for 1 span, is that load, and the span is that dimension there, from there to there. At the center it was WL, well, I've drawn it the wrong way, guys, sorry, let me correct that. At the center, the negative moment goes down like this. Because over here it's WL squared over 11. That reduces it. If the denominator increases, the result is going to be smaller. And we've got WL squared over 10 over that support. Those are the negative moments. Again, as I said, I ignored this one. The positive design moments shall be taken as follows. In an end span, in any end span, WL squared over 11. So what they're saying is from there to there is WL squared over 11. At interior spans, WL squared over 16. WL squared over 16. Now if you just had to sketch in a bending moment diagram, it would look like this. And it's only 16 there. 16 there as well. And WL squared over 11 over there. And the bending moments that you're concerned with are the ones I'm shading in. These are the important bending moments. Okay? And we'll be looking at that further. Then you can look at the transverse design shear force in a member, also from these tables. Shall be taken as follows. In an end span, this is an end span, this is an end span there. At the face of the interior support, so I'll just redraw that. beam, looking at shear. Okay. Looking at the transverse design shear force, they give us coefficients for working those out as well. So that's the shear at the face of one of these columns, because you could assume that these were columns or beams or whatever they were, but probably beams, transverse beams. Now, at the face of the interior, this is an interior support of the first interior support, 1.15 times the total load on the beam. So this is 1.15 times the total load on the beam times big W, total load on the beam. In an end span, at mid span, the shear is WL/7, we're not interested. And at the face of the end support there, it's just the total load, and the half of the total load in the beam is the shear force at this particular point. In interior spans, these are two interior spans on a 4-span beam. At the face of the supports, WL/2. So that's pretty straightforward. Shear there's WL/2, 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 and WL/2. Because of symmetry, the one over here again is exactly the same as 1.15 times W, total load. The mid-span shears are there for academic interest. They're very small, as you can see, 1/7 and 1/8, so I wouldn't worry about those too much. But this will all crystallize as we go through the tutorial today. Thank you.